Okay. So let us continue with the chapter number 5 here is a factorial experiment. So I have discussed with you all is about the factorial analysis, means that they involve more than 2 factors, okay, or more 2 and more factors and onward. Okay, so I have discussed with you the 2-factor factorial analysis, where the 2-factor factorial analysis will include the mean factors as well as the iteration factors. And then I also show you the example to show you that when the iteration effect is significant, okay, let's say the example where is an example 521, where your iteration will be significant, okay, means that you cannot reject the iteration, then your conclusion will be lead you to the different conclusion. For example, if in this plot, as you can see that in this plot, we will choose the level 3. We will choose the level 3, okay, or the material type is a 3 because they give you the highest life of the battery, as well as if you choose the temperature at the 15 degree, then they give you the highest life. Okay. However, if your iteration effect is significant, so your interpretation may not be correct. So this one will show you in the following diagram here. If you check out at the temperature number 15, then we should be use you want to get the highest mean life of the battery, you should be choose type number 2 instead of the type number 3 here, as show you here the combination. So therefore, the iteration will be very important in analyzing the factorial analysis. So we always need to check whether our factors, our iteration factor is a significant or not the significant. Okay. So after I show you the example of the 2-factor factorial analysis, then I go through another example is where if we also can be assumed that there are no iteration factor there. Okay. Obviously, how we want to know that is no iteration effect. Of course, we can test the hypothesis. We can have a model, the full model first, means that include the iteration. Then after that, we test. If they're not significant, then we can reduce our model to just the mean factor only, without the iteration factors. Okay. So this one is where you have I discussed with you. So if you do not have an iteration factor, then all the sum of square from the AB iteration will be combined together with the error. Then they merge it to the sum of square for the new error here, where your sum of square plus A and the B, you will get your sum of square for the total. Okay, so this one is what you have in the analysis of variance. Then I also go through with you, if you do not have an iteration effect, then of course your fitted equation will be given by here without the iteration factor there. Okay. Then after that, I also mentioned to you all, if we willing to have only single observation per cell. As I mentioned in the earlier a few slides, I have mentioned that when you want to run your factorial analysis, you need to have a replicate is more than 1. Okay, because I also show you that if the replicate is equal to 1, your sum of square for error will be equal to 0. So if you have a sum of square for the error is equal to 0, so you cannot be perform the analysis of your F-test, because your F-test will be equal to if you only have a MSA over MSE, or you have a MSB over MSE. But if your SSE equal to 0, therefore you can't find your MSE. So in that case, you cannot perform your F-test to test whether the factor A or factor B is significant. Okay, so this one will happen is if your N is equal to 1. But in this section, I also told you that if you still insist to have N equal to 1, then you need to lose certain information. So the information you will lose is about the iteration. So if you want to have N equal to 1, so your iteration here, you need to certify it, make sure that they are not significant. Okay, so if you're in that case, you can have a following one. when you have a n equal to 1, the SSE will equal to 0. So therefore, your SSAB, you can treat it as an error. Okay, it's become your error, or the SSAB is or the AB is not significant. Then we can use it as the testing or using as a MSE. Okay, so therefore, when you perform your F test, you have a MSA over MSAB, MSB over MSAB. So this one, the sum or square here, they can become your sum or square for the error to replace the error. Then you can be test the factor A and the factor B. Of course, you will lose the information is about the sum or square for the AB. Where the sum or square for AB, you cannot be say that you want to test it because you don't have the SSE. Okay, so this one is the information you need to lose if you're willing to you want to run only the n equal to 1. Okay, so if you want to get the more information, of course you need to have more replicates. Then of course clearly if you have an n is more than 1, then you can be estimate your SSE. At the same time, you also can be get the more accurate answer if you have a more sample size. But of course, if you want to take more sample size, then you need to have a time consuming. You need to run many experiments. Okay, so everything also you need to consider whether you want to have results of them or you want to get a more accurate here. Okay, so this one is what we have discussed in our last lecture class. Is only for the single observation per cell. Okay. So this one is an analysis of variance table. If you have only single observation, as I mentioned, the sum or square for the AB will become this part. They will replace with the residue here. So therefore, you will call it as a MS residue. So when you want to perform for the testing of the A, is the A divided by MS residue. If you don't want to use the name residue, you can be use the MSAB also possible. Okay, this one is just a name. As long as you know that your test is belong to the F is the MSA divided by MS for the AB, or the residue also can. As long as you know how do you take the ratio. Okay. So from the two-factor factorial analysis, we can be extend the idea to the 3 factors, 4 factors, and so on. So the only thing the difference is when you have 3 factors, then you need to consider all the iteration effect there. Okay, for example, if you consider only 3 factors, you have a factor A, factor B, factor C, and then you have a AB, AC. After that, you have a 3-factor iteration is a ABC. So altogether, you have a 6 component of them. Okay, you have a ABC, AB, AC, okay, AB, and then AC. And then you have BC, BC, and then you have another one is ABC. So you have so many of the component of the iteration. So especially when you have more than 3 factors, 4 factors onward, as you can see that your iteration effect there, they have many component of iteration. Then when you want to interpret the results, will be very difficult. So the idea is just extend it to the many factors. So this one is one of the example where I show it to you is just 3 factors where you have tau is for the factor A, beta is for factor B, gamma is for factor C, and then this one is the tau beta is for the A and the B, tau gamma is the A and the C, and then beta gamma is your B and the C. After that, you have a tau beta gamma. So you have a 3 iteration. So your model will become complicated. Especially you want to analyze on the which combination you want to choose to optimal your solution. Okay, so because of the iteration here is a significant, therefore you may need to analyze it slowly, okay, or analyze it carefully. So for your information, most of the time the high order iteration will not significant. Okay, especially when we go to the higher level of the factorial design. But of course, this one is must depends on case to case. Okay. So for the here the general factorial design for the 3 factors can be given as a following one. Okay, we will expect that if the 3-factor iteration and the 2-factor sum of them is not significant. If they are not significant, it's much more easier. You want to analyze for your tau, beta, and gamma. Because what you are interested in the whole study is about your main factor, your tau, your beta, your gamma. Okay, you want to know that is there any significant difference if I use a levels of factor A? Is there any significant difference? Is there any significant difference when I change the levels? Is there any significant difference when I change the different level of the factor C's? Okay, so this one is all your main target. But because when we formulation of the model, all the iteration factor will be included in the model. Okay. Then of course we will hopefully all these iteration were not significant, so means that their sum of square can merge it to the error. So you can be from your model of the full model, you can reduce into the certain model without the iteration factors. So this one is similar to what I mentioned before, where you have the assumption. This one is they assume. Of course, we can be test it out. Okay, they without the iteration. So this one is a sum of square. I believe that you all will have seen before. This one is a sum of square for the factor A until the factor ABC. Of course, because your n is more than 1, then you have a MSE here. Okay, so all the test statistic, as you can observe it here, is a MSA divided by MSE. Okay, it's divided by MSE. Okay, so all the testing we can be based on the F distribution to test. Then you can be from the complicated model or the full model with the factor A until the factor ABC. You can be reduce it to the complicated, the simplified model. Those of the not significant one, you can be remove it away. Okay. So this one is for the general factorial design. Okay. So this is one of the example from the textbook. Okay. Where you involve the in the example 5.3, where they want to study is 3 factors here. The first one is they want to know that the first factor will be the percent carbonation. The second factor will be the pressure or operating pressure. The third one will be the line speed. So they want to know that whether these 3 factors will be affected your final outcome or the yield of the results. Okay, so this one they will study for the 3 factors analysis, and then based on the 3 factors here, they also concentrate on the 2 replicates. Each one will have 2 replicates here. Okay, so therefore this one is a 3-factor factorial design. Okay, so it depends on how many factors is you need to check out your experiment, how many factors you are concentrate. Okay. So this is the data you have. So for the factor A, they consist of the 3 levels. Okay, whereas the factor B, they consist of the 2 levels, as well as the line and the speed. For the factor C, they consist of the 2 levels here. So they run the experiment under the certain combination. Okay, under the combination for the 10% with the pressure is 25, and then the line speed is 200. Then they run the experiment. They obtain the following result. It's 2 data here under this 3 combination. So another combination will be here, another 2 results. Okay, because each one they repeat for the 2 times. Okay, for the n will be equal to 2. For the A will be equal to 3 because it consists of 3 levels. For the B will include the 2, and then the C also 2. Okay, for the 3 levels, 2 levels, 2 levels, and then number of replicate is 2 times. Okay, so this one will be the value of here, and then this one is the value of here. Okay, and then similar thing for this one. Okay, so the bracket here is of course when they want to calculate the iteration effect, they need to use the value of the here to calculate the iteration sum of square. So they put the bracket here is referred to the total of the -4 and then total of 1 and so on. Okay, so at the same time, they also want to write it out because you study the two-factor iteration. You have a AB, you have a AC. Okay, you also have a BC. So therefore, they just leave it for you. What is the total under the factor A and the factor B? Okay, so the total under the factor A and factor B at the 10 level and the 25. So the total value is -5. So how to get it? Under the level A and the pressure 25. So you total out this part, you get the -4 plus -1 is a -5. Okay, so this one is the total under the AB total. This one is AC, the total under the AC. Okay, so based on here, this is I use R code to run it out. Just a summary. I have keyed the data here. You consist of the percent is 8 data, and then after that this one is 8 data here. And then if the pressure 25 is 12 data, the 30 is 12 data as well. And then this one 200 also 12 data, 250 also 12 data. This one is just help me to summarize only. Okay. After that, for this one is the ANOVA table. The ANOVA table is where we study for 3 factors, and then we want to run for the full model. What I say the full model is means that you include all the single factor, and then you have an iteration, you have a 3-factor iteration. So I will put the multiply here, then they can run for me the full model. So as you can see out, this is a full model analysis. Okay, so before we go to the F test here, you can see that the sum of square component here. The sum of square is let you know that how much the deviation or the square component they contribute come from the percent. So as you observe it over here, the sum of square is come out from here. Of course, you have another one is called the sum of square for the total. Okay, you have a sum of square for total. It means that you total out all these sum of square, you get one value of the total here. So out of the sum of square for the total, they distribute to the here. So as you can observe it here, you also will roughly guess that the 3 iteration effect is only contribute just a one unit. For the 2 iteration also is 1 unit, and then this one is percent and the speed is only 0.5. Okay, and this one, the 2 iteration will be here. So clearly we can see from here, your percent, pressure, and the speed for the factor A, factor B, and factor C here, they contribute quite a lot for the sum of square, whereas those of the iteration is they contribute just very minor, and then since that they are not really the significant. Okay, so first thing we just analyze for the sum of square first. Then after that, once we analyze the sum of square, then we will go to the testing the hypothesis. Okay, so the F test here is if you want to refer to this value, of course we need to compare with the table values from the F table. But because the statistical output will give you the p value, so based on the p value here, clearly is consistent to what we are expected. These 3 have a very high value of the sum of square, so therefore they have a significant. Okay, may not be say that they may high, then is considered as a significant. We still need to consider testing the hypothesis. So after testing the hypothesis, we found that the percent, pressure, and the speed. Okay, these 3, the percent, pressure, and the speed, all are the important factors. Then they are important because the sum of square here, and then at the same time you're using different percentage, you're using the different pressure, and then you're using the different speed, they will give you the different results. Okay, because here show you the significant, and then some more, all these things is not significant at all. So this one is considered as a good sign because you want to interpret for the percent, which percent you should be used to optimize your solution. Then you can be just compare alone only. We no need to care about whether how about the pressure, how about speed. because all the iteration is not significant. But if the iteration is significant, then you need to consider part by part. Okay, you cannot consider together. Okay. So this one is what you have here. Clearly, here is just show you that the percentage of the significant, show you that this three is significant, the rest of them not significant. So for the F value here, the F value for the first one is obviously is equal to the mean square is a 126.38 divided by the mean square from the error or the residue is equal to 0.71. Okay, so this one is referred to your F value. Okay, your F value if you want to test the hypothesis. Okay, so I think the examples I have mentioned to you in your previous tutorial, you also have calculate how to calculate sum of square for the A, sum of square for the B, sum of square for the C. All of them will be quite standard formula. Okay, and then sum of square for total, you also will see before. Okay. So just now our result will show us that only these three factors were significant, and then the iteration is not significant. So when we want to analyze the mean plot, then we can analyze it separately. Okay, so for the first plot, we are referring to this one is the first one is I think the diagram. Okay, the first one is refer to the percent. The first one is refer to the percent, the pressure. Okay, the pressure here. Here I think the words is the pressure is missing because the percent is here, the speed is here. So because this one already closed it, I will put it here. This one is refer to the pressure. Okay, so under the different pressure, they will give you the year of the higher. Okay, if you want to have the deviation will be small because you want to know the average field deviation. So it's close to the 0, then I should choose the smallest. Okay, so in this case, if we want to have here, you want to have a closer to the 0 here, then we should choose the pressure at the 25. And then for similar for the percent, we want to choose the closer one. Then of course, is you can check it out. This one is -1, so here should be the smallest or the closer to the 0. And then this one is here is a low closer to 0. This one is higher, so we should choose this level. So because of the iteration is not significant at all. Okay, only the main factor will be significant. Therefore, if in this case, I will choose if I wish to get the closer to the 0 or the minimum, then I will choose the 25 at the pressure 25, and then the number of percent is 10, and then you suggest to another here is 200. Okay, the 200 is for the speed. So these are the three conclusions you can make based on the analysis. But if you have an iteration is significant, of course you need to analyze it, take care about the iteration, and then you need to analyze it separately. Okay. So here is doing for the plots to get the plot for each one. Okay. Okay. So this example will be show you the plot here, and then of course here will be show you the iteration plot. Okay, if you wish to have an iteration plot. Okay. Okay. So because the result here also show you that the iteration is not significant. Okay, if they're not significant, it means that they are almost symmetric. I mean the parallel. The line will parallel. So this one is what we were expected to get it. Okay, if for the different temperature, you vary the temperature, and then you have two different of the factor levels. As you can see out, your pressure, here is this one is for the pressure 30. This one is for the pressure number 25. Okay, for the average deviation here. So inside here, both of them is a parallel. This one will be expected in the ANOVA table to show you that they are not significant. So you will get parallel. if you have a crossing, if your iteration is significant, then you will expect your graph will have a iteration. Okay, when you're plotting the graph, you have a very iteration. Okay, for this one is very obvious, especially your p-value there, whether the significant is mild or not the mild one. Okay. Okay. So this is a Minitab results. Okay. So the Minitab results also show you that the overall models. Okay. On top of the overall models here, in the Minitab result, they also show you that the R square and the adjusted R square. How good is the models if you consider all the factors inside? Okay, if you reduce some of the iteration, then how good is your model? This one is, of course, is from the Minitab. Okay. And then over here, this one is a plot similar to just now one. If I use a Minitab, they can show me using this way. Okay. And then this is the iteration plots. Okay, all the three lines is nearly a parallel, even though these two is not nearly the parallel. Okay, but they are towards the in general they are still look like it's parallel. Therefore, your iteration is not significant. Okay, if you can clearly find out there is a crossing, then your iteration effect there it should be significant. Means that there is a significant difference in the iteration. But as you can see from these three plots, almost all of them is a parallel. So therefore, we will expect that the F table, the ANOVA table, show you that the iteration is not significant. Okay. So for the higher factor one, we need to do it slow one by one, of course here. Then for the model, since they are not significant, I can reduce the model to only with the three main factors without the iteration. Then I rerun the analysis of variance again. Okay, I will run because they are not significant. So I can reduce it to the only the main factor, factor A, factor B, and factor C. Okay, then those of the iteration sum or square, they will merge it to the error here. Okay, so in this model, also, of course, they will show you that the percent, the operating, and the line speed is a significant difference. Then on top of this thing, as I mentioned also, you can see the R square here. Okay, of course, the R square is not in our course here, but I just compare with you here. You can see that if you put in all the model, all the full model, all the iteration here, you will get your adjusted R square is a 95.16%. Okay, means that your model, your total variation of the Y can be explained by model is around 95.16%. Okay, but if I make the model will become the here where the iteration is no longer in the model itself, then you still get around 94%. So this one it means that if I only need these three variables, and then I can be model it very well for my Y. So you will get your very high R square. Even though they reduce by the 1 unit, but it's still acceptable instead of you are deal with very complicated model. But of course, this thing is just a result from the Minitab. I do not cover all this R square in this course because this course is just study the analysis of variance. Okay, but because the analysis of variance, they consist of the linear model. So the linear model will related to the R square here. So therefore, you may need this information. In the output, then they will show you here. And then if you have a Minitab output also, you can see that S. What is the S? S is just a standard deviation. Okay, so how to read the S here? Okay, how to read the S here? If you still remember, I have mentioned to you before, we have an expected of the MSE will equal to our sigma square. Okay, we expect that MSE will equal to sigma square. So therefore, we use the sigma hat square. You're using the MSE to estimate it. Okay, you want to estimate your variance. Okay, so the variance here will be using the MSE. So therefore, this S here is actually equal to, in the output here, S is actually equal to the square root of the MSE. Okay, If you have a square root of the here, MSE is a 0.866, then you can get 0.93. It's the standard deviation. If you're aware of that, this one is the standard deviation, so it's actually the square root of MSE. So this part is just tell you that the overall standard deviation is how much only, okay? If you need to use it, then you only use it, okay? So therefore, when you use a different software, they will give you the different results, okay? They will give you the different results. And then their presentation, the username will be different. For example, just now you can see here, inside here is actually your error. They call it an error. But you using other output, they may call other name. Okay, in the ANOVA table here, they call it as a residue. So you don't confuse this residue and the error. In fact, they are the same. Only the different software, they use a different name. Okay. So this one is here. Okay. It's the same output from the two different software. Okay. So after the factorial, the 3-factor factorial design, of course, you can be extend it to the 4 factors, 5 factors, and so on. Okay. So under the factorial design, we also can have the Nelson factors. So Nelson factors, how we want to eliminate the Nelson factor, or we were using the technique is a blocking. Okay. So the blocking here, this one is your this one is your blocking here. Okay. So where the delta K is a K block, and assume that iteration between the block and the treatment is negligible. Okay, so we will have don't have the iteration in between the blocks with the main factors. Okay, so under the block here, I have mentioned to you that we try to for the Nelson factors. Okay. So therefore, if you have a Nelson factor, then you need to consider the block here. Okay. So this is I do not read it one by one. Actually, this one is one of the example of the here. Okay. So they have there is a factor here. Is a ground cluster. Is a low, median, and the high. And then the filter types you consist of the 1 and the 2 here. Okay. But because they're using the different operator, therefore this one is become the 1 block. This one is become the 2nd block, the 3rd block, and the 4th block. Okay, because the operator is not the main target of the studying for this experiment. The main target is they want to know the effect of the filter type and the ground cluster on the yield of the results. So therefore, this one is they have a operator because they use a different operator and then operate it out. If you think that the operator will be is a skill operator, so you do not have any effect on it, so you don't need to consider this one as the Nelson factors. Okay. Okay. So this one is an analysis where they can show it to you. Okay. Of course, we just refer to the main thing is the ANOVA table first. So in the ANOVA table, this one is belong to the block here, where we have here. This one is a block here. Clearly, you can see that the block here is a significant. So means that I using the different operator will be affected my results. So you have extract it out for the block. So in the analysis, this one you have a sum of square for total will equal to sum of square for the factor A plus a sum of square for the factor B plus a sum of square for the AB plus a sum of square for the block plus a sum of square for the error. So the sum of the square for the block here will be get it from the here 402.17. Okay, you either use here or you here. Okay, you have this thing. So this one is the sum of square for the block here. And then once you get the sum of square, you get the mean square by divided by their degree of freedom. Then you can test the hypothesis. Here clearly show you that they are significant. Okay, so therefore the blocks is you need to take it out from the sum of square. If you're not aware that the operator is a significant, then you may merge these two together. these two components, you merge it together, then you are testing. So this one will lead you to the inaccurate results because your sum of square become larger. Okay, so when you take the ratio, then you will have you divided by the different ratio. Okay, so this one is a similar idea for the blocking effect in our previous chapter, chapter number 4. I believe that after I have gone through with you the blocking in the chapter number 4, some of you may get the idea what is meaning by the blocking. Okay. So instead of the have all this factorial design, actually all these things we can be write in the equation. If you have a textbook, you can see that they all write in the equation. But here I do not include the equation first. What I say equation is means that the linear model equation. I will leave it all the equation to the chapter is called response surface methodology. Okay, I will link it to that and then I have a new equation. So here I just concentrate on for the every design, we concentrate on the what is the model you have and then how to get the sum of square, then how do you get the fitted equation, and then you have a residue, and then how are you going to test it out the ANOVA by using the MSA divided by MSE and so on. Okay. So this idea of the here will be similar from you once you first day you follow the class is a one factor, okay, or the one way ANOVA. You only study the single factor with the different levels. Then after that you have the second chapter in Minjet chapter 4 where you have a Nelson factor will go in, where the Nelson factor is not your main interest. Then today you go through is a factorial design, where the factorial design you will study many factors at the same time. Okay, but as I mentioned, if you study the many factors at the same time, you need to consider all the iteration. But sometimes before you run the experiment, or you also can be assumed that those of the higher order iteration, you can be go to the 0. Okay, or when you have a n is equal to 1, only single replicate, then you can be assumed that those of the high order iteration will be not significant. Okay, then you only can be test the analysis, or you can be perform the F test. Then you can be check whether the factors your study is whether significant or not significant. Okay, so we do not have a definite answer is how we want to know higher order is significant or not significant. It depends on how much information you're willing to lose. For example, if you only test for the n equal to 1, then definitely you know that sum of square for the error you cannot estimate. So therefore, you need to give out certain information. So for the high order iteration, most of the time they are not significant. So therefore, we can be remove it. But if you check it out in this example here, okay, the two-factor iteration, they are nearly not significant. If you test the alpha is a 5%, then it's not significant. If you test at the 10%, then it's significant. Okay, so it depends on the test you're going to test. What is a significant level you select? Okay, so this one is until this part. This one is the last slide for the chapter number 5. Is a factorial analysis. Okay. So after the factorial analysis, we will go through one more chapter. This one? It will be very useful. Okay, it's called the 2 power of k factorial design. So I believe that one of the students before that have shared the link of the textbook, so you can be read it out more detail, because what I explained to you is I just take out the summary. Okay, but if you want to read in more detail about the scenario, especially the engineering examples, they tell you the whole story, how they from the beginning until the end, how they collect the data. Some of the example they will tell you, okay, how the data is behaved, how they want to monitor in the real case study. Then you can read through the textbook. Okay. Okay. So this one, the chapter number 5 later on, or upload inside the text inside the Spectrum or in the Microsoft Teams. Okay. So one reminder is those students who are don't have the background on this analysis of variant. I hope that after this a few weeks you can be managed to get the idea. Then as you can see our idea is just break down the sum or square to the different component, and then we do the analysis part by part. Okay. After the chapter number 5 is a factorial design. In the chapter number 6, we also go through the factorial design. But in this factorial design, we will concentrate only the certain case. Okay, under the certain case, it means that you only have a 2 power of k factorial design. So what is meaning by the 2 here? The 2 here is means that every of the factors where you have a k factors, every factors only consists of the 2 levels. Okay, so we only concentrate on the certain factor levels and then where it consists of the 2 levels. So under the 2 levels here, we can be grouped them as a 2-1. We call as a low level and the high level. This example I have shown to you during the beginning of the factorial design. I have shown you together in this diagram. Okay, you study for the low level and the high level. So this one is what we are concentrating today. It's just the 2 levels here. You can go to many factors, but we only concentrate on the 2 levels. Okay, so the 2 levels here, they can either the quantitative or the qualitative. Okay, you can say that is a low and a high, or you can say that is a 20° and the 30°. So this one is what you are going to analyze. Okay, so the 2 levels can be either quantitative or qualitative. So they are actually is very widely used in the industry experimentation. Okay, of course, they widely used. It depends on that industry, particular industry. So actually, they form a basic building block for other very useful experimental designs. Okay, so these 2 levels here. Okay, actually these 2 I can merge it together. They concentrate on the 2 levels here. Sometimes you study for the 3 levels or 4 levels. Okay, you have every factor you consist of the 3 levels, 4 levels, or 2 levels, and so on. So instead of study many levels, they only concentrate on the 2 levels where we try to get the minimum and the maximum levels they have. Okay, because they want to do it for the factor screening experiment. You just concentrate on the lowest and the highest. And then if the lowest and highest also there is a significant, then you can suspect that that particular factor will be important in your analysis. So therefore, these 2 power of k factorial design, they also call as a factor screening experiment. Okay, let's say I have a 5 factor here. I have a 5 factor A, B, C, D, E. We'll have a 5 factors. How we want to take? If you use a general factorial design, of course, you need to run all the 5 models and then all the iteration here. So instead of the study the factors and then you have many levels, we do not know which one will significant or no. Then they just concentrate on from the smallest here and the largest here. Here we only study for 2 levels. Then based on these 2 levels, we will decide whether this factor will be very important or not. If they're really very important in your study of the 2 levels, then we can be study in detail about the levels inside that. Okay, so therefore the 2 power of k factorial design is considered as a factor screening. So after you screen it out, you can be doing for the very useful for other experimental design, because the 2 power of k factorial design can become the 2 power of k fractional factorial design. Means that you only run for the certain fraction. So they can be useful for other design as you perform the factor screening here. Okay. So the example here, the 2 power k factor example, when you calculate the sum or square, all these things will be the similar to the factorial design, the blocking design, where you calculate your sum SSA, SSB, SSAB, and so on. So our working will be the same. But because of this thing is a 2 power k factorial design, there is a special case. So the computation also can be simplified out. Okay. So we consider this one is an experiment where the factor A consists of the low level, we use a notation minus, and the high level we use a plus. Or sometimes they use a 1 and the 1 here. Okay, either it's a +1 or -1 to represent the low level and the high level. And then the B here is also you have a low level is a -1, +1. Okay, to represent the low level and high order, high level. Okay, so here if I put the negative, it refer to all of them at the low level. If I refer to the plus, means that is at the high level, then minus is at the low level. So these are all the combination. For each treatment combination, we have 3 replicates here. We repeat for the 3 times. Okay, so the n will be equal to 3, the A will equal to 2 level, B also is equal to the 2 level. Okay, so you have n is equal to 3 for each one, you repeat for 3 times. So in this example is refer to the chemical process example. So your factor A is referred to the concentration, the factor B will be the catalyst amount, the Y will be the recovery. Okay. So in the here is a simple case of the 2 power of the 2 design. Okay, so the is equivalent to the 2 power of k, where your k will equal to 2. Okay, means that is a 2 factor. Okay, the k will be equal to 2 is a 2 factor design here. So here will be similar to I just label it to the total of here. So again, another thing beside the plus and minus sign here. Under the 2 power k factorial design, we have a special notation to represent it. So because this 2 is at the low level, we use a notation on all the factor levels at the low level, we use a notation is a 1 to represent it. Okay, the bracket of the 1 to represent it. So once you see the under the 2 power k factorial design, 1 here is you know that all the factor under study with the low level. Okay, those of them at the high level one, we label their alphabet. For example, the A at the high level, so you use a notation as a A. For the B at the high level, we use a notation for the B to represent that this one is a high level, is a occur in the factor B. Then if both of them is a high level, we use a AB to represent it. So this is a notation to represent the treatment combination. Okay, so this notation you can see from here, where you here is a 1 here. Okay, the A here, and then the B here, and then the AB here. So once you see the AB, you understand that this both of them is at the high level. Okay, so the value of the 1 here, instead of the meaning of the level they are located, they also have another meaning is the total out the observation under this category. Okay, so the total observation will equal to 80. So this A1 here is a total for the 80. A here is a total for the at the A at the high level, where else the rest of them at the low level. AB here is the same for A at the high level, B also at the high level. Okay, their total is equal to 90. Okay, so bear in mind that you know this is a notation for all these things. Okay, so the plus and minus denote the low level and high levels of the factors respectively. Low and high are arbitrary terms. Okay, you not necessarily must use a low and the high here. Okay, so geometrically the 4 runs form the corner of the square as you can see on here. So factor can be quantitative or the qualitative. Okay. After that, although their treatment is in the final model will be different. Okay. So this one is a new notation you will consider here. Then besides here, as I mentioned, 1 here is a total for here. So we can be refer to the 1 here is a total is 80. A here is a total for 100. Okay. So under the 2 power of 2 factorial design, when we want to label the A and the B with their minus and plus, we need to have a systematic way of the present it. What I say systematic way is means that when you want to label it the factor A, B, you need to starting from the minus 1, then you plus 1, okay, for the factor A, and then you have a minus 1 and then plus 1. Okay, so you can see that they are alternate. Minus 1 plus 1, minus 1 plus 1. If you for a factor B, you have a 2 minus together, then 2 plus together. Okay, there is a systematic way to write it down. Later on, I will show you to you if you have a 3 factor A, B, C, then you can see that when you list down, you can be list down all the possible combination. Of course, number of combination is just 2 power of 4. 2 power of 2 is equal to 4. If you have a 3 factor, is a 2 power of 3. Altogether, you have 8 combination. Okay, then you need to list down all the possible cases you have. Especially if you have a 4 factor, then it's 2 power of 4 if you have 16. Sometimes if you not list down in the proper way, then you will miss out certain combination. Okay. So I have introduced this thing. I have introduced to you what is meaning by 1, A, B, and AB here. Okay, so this one is for the refer to the total. At the same time, the bracket 1 here is refer to all at the low level. Okay. So this is a diagram here. Okay, if you cannot follow, here I will show it to you. Okay, the height level of any factor in the treatment combination is defined by the corresponding lower case, and that the lower level of factor in the treatment combination is denoted by the absence of the corresponding letters. So as shown in the previous diagram here, the symbol 1, AB are now representing a total of all n replicates taken at the treatment combination. If for the 1 here is a total out for the all of them here there is a dot here because the third dimension here or the third position here is referred to the number of replicate. So you find out the total under this one at the low level. This one is a A at the high level, so you have a Y12, then dot here. Okay, and then the B here is a 1, 2 here because the B is at the high level, so therefore here is a 2 here. And then this one is AB is equal to both at the high level here, then it's a dot. They total out. Okay. So now we try to link it out with the total here. So remember that the AB is stand for the total under the combination, the treatment combination AB. Okay, so now based on here, if we want to study the effect of the A at the B positive, so this one is how we want to do it. Is let me see, the diagram is not here. Okay, maybe I will show you here. Okay, I diagram, I will show you here. This is the diagram here. The question is asking you, okay, if you want to looking at the if you want to looking at the effect of the A at the B positive, at the B positive, the effect of the A, this one is a factor B. Okay, maybe I will put it here. I will put it here. I put the diagram here again. Okay, whether you want to put the plus minus 1 also can, or you use a minus and plus also can. Okay, this one is for factor B. Okay, so this thing, this one, the notation is a 1. This one at the height level of factor A is a A. This one is height level at factor B. I use the notation B. This one is a AB. Okay. So if I want to know the effect of the A at the B positive, the effect of the B at the the B positive, so you refer to the B positive. What is the effect of here? So it's a AB minus a B divided by the N here. So you will know that from here to the height level here, I mean from this level to this level, what is the changes? Okay, so you have use the AB minus a B, so you will know whether it's a positive or negative, or the value is 0, it's no different. Then divided by N, because for the average value of here, the AB of here is a total. The AB is a total under this cell. In the previous example, the AB, you want to get the total of AB, you base on the N is equal to 3. Therefore, you need to take the average value. You divided by the number of the observation you have. Okay, we just consider the average value. Okay, or you can see that this one is just a AB over N minus the B over N. Okay, just the average value. Okay, so again, another thing, if you want to know the effect of the A at the B minus, from the B minus here is a A minus by 1. Okay, divided by N, again the same thing. Okay, so this one will we know the effect of the A at the B positive, the effect of the A at the B negative. Okay, so after that, we want to average this quantity yield the main effect of the A. So you take the average value of all these two quantity, then you will get is a here plus the another thing, you take the 1 over 2 here, then you get the following formula out. Okay, so this thing, this formula of the effect, if I'm not mistaken, I also have mentioned to you before in this part. But in this part, I'm using the other way. I want to know the factor of the A and the the effect of the factor A at the positive and the negative. So how I do it? I just use the factor A at the height level of both. Here at the height level, low level. So I get the difference. You can see that you just take the average value of here minus away the average of here. Then you get your effect. Similarly, this concept will be the same. Okay, but this one is I just mentioned to you the here effect of the difference of here. I just tell you the difference of here, and then I take the average value of that here is divided by 1 over 2. Then you can get the effect of A. So in general, as you can see out, the effect of A is just a 1 divided by 2n, AB plus A minus B minus A. Okay, so this one is what you have in your effect of A. Similarly, if you want to go for the effect of the B, if you want to find the effect of the B at the A positive, so you refer to the A positive here, you use the AB minus the A divided by N is what you get here. If you want to looking for the effect of B at the A minus, you will get is a B minus 1 divided by N. So you get here is B minus 1 divided by N. You get the following one. So finally, you will get your main effect of the AB will be given by these two. You take the average value, you will get 1 over 2n AB plus A minus the AB plus B minus the A minus the 1. Then you can get the effect of the B. Okay, so from here, I have shown it to you that I have an effect of the A, how to calculation of the effect of A, how to calculation of the effect of the B. Okay, after that, you also can be count out the iteration effect. Of course, we use the average value of the cross product. Then you take the overall average, you will get the following one. Okay. So if you observe it, what you have before, you have a first one. This one is the first formula I consider. This one is the first formula I consider here. And then after that, you have another formula is the effect for the B. Then the third one will be the effect of the AB. So all of them will based on the AB plus 1 minus A minus B. And then here is the AB plus B minus A minus B. So how are you going to memorize? So this one, the effect here is actually related to the table. Okay, it's related to the just now the table what you have it before. Okay. So I go through one more slide first. before I go through it, the effect, I think I will put all these effects in the following table. Okay, so this one is I show you how to calculate the effect using this way by using the average value of here. Then you the difference in between these two at the positive level and the low level, and then after that you take the average value, you get the effect A. You can do for the B and the C as well is here. Alternatively, you also can be used previously where I tell you in the chapter number 5 here. You just take the average value of the high level and the average value of the low level. You find the difference. Then you will know what is the effect for the factor A. So in this case, also the same thing. You find the average value of the at the high level and then at the low level, you get the difference. So they will lead you to the same formula. Okay, the effect A, the effect B, and the effect C. Okay, so once you know the effect of the A, B, C, so you know that if the answer will calculate for the A is 8.33. Okay, so this one is for the positive effect. This one will get the negative effect. And then this one, the iteration effect will be just 1.67. Okay, for the effect itself, you can't tell much on the value here. Okay, this one will tell you that they have a positive effect only. You are from the low level, from the high level to the low, from the low level to the high level, you have a positive effect. For the B here, it means that you're from low level to the high level, you have a negative effect. So where the iteration in between these two is a 1.67 is a positive. Okay. So the effect here, using the two different techniques, you can calculate the effect. Okay, you can calculate the effect using the following formula. Okay, so now I try to link it to you how this formula will be useful for you to calculate instead of memorizing this formula. Okay, this one will related to your sign table here. This one I call as a sign table here. So if you still remember just now I teach you the way of you write your effect here. So we put the low level, we will put the minus, plus, minus, plus here. Okay, so we are starting from the minus, plus, minus, plus. And then the factor B here, you put the 2 minus, 2 plus. So how you want to know the AB here? To get the AB here, then I will multiply the AB, the iteration here. I just multiply the sign here. -1 times negative times negative, you get positive. Plus, minus, you get the negative. And then here negative, here positive. So the AB here is just multiply the sign here. So once you get your factor A and the factor B and the factor AB, you know that the factor A at the low level, you use a notation 1. Plus and minus, you had level at A, so you use the A here. Then here is a B, here is AB. Okay, so you represent in the following form, then this one is called the standard order. You starting with the minus, plus, minus, plus, 2 minus, 2 plus, then obviously you will get your standard order. Because if you're starting in this way, your 1 will always the starting. Then followed by AB, and then you multiply, you get the AB. This thing is called the standard order. Okay. So from this table, what is the useful of the plus minus sign here? So if you observe that here is a minus sign, then corresponding to the 1 here. And then here is a plus sign under the factor A, corresponding to the A, and then minus sign with the B, and then plus sign with the here. So what you can observe from this part here is actually useful for you to calculate the just now what you can see from here. This one, and this one. Okay, they are very useful. You can see the plus minus sign here. So all these AB and AB were related to this table. So let's say the factor A is a minus. Minus is 1. Plus A. Minus B. Plus AB. So you can see that is minus A and the minus B. So you can see the factor A here. Minus B minus 1. So it's actually is referred to this part here. So therefore, this one is just the idea how do you get the effect. But when you want to start calculation, you can see this thing is get from the table here. So this table will tell you if there are two minus here, is a 1 and the A is minus. So you can see the factor B here, A and the 1 is minus. AB and the B will be plus, so it's a plus. For the factor iteration AB, A and the B is minus, so you can be referred to here, A and B is minus. So this one is equivalent to here. So what is the name of this thing is called? I will put it in the following slide. What I call is called the contrast. So the contrast of the A can be get from the table above. So you have minus 1 plus A minus B plus AB. For the contrast B is a minus 1 minus A plus B plus AB. And the contrast for AB will be given by this thing. Okay, so when we want to write the contrast, if you can form the following table here, even though you have a 3 factor, 4 factor, 5 factor, and so on, if you can form the plus minus sign, follow the standard order, then easily you can calculate their effect. From the plus minus sign here, with their treatment combination here, you will know what is your contrast for each one. So the contrast, what I mentioned, is a contrast here. Okay, I call it as a contrast here. And then from the contrast here, you just put inside your A is equal to 1 divided by 2n. Then you can get out the effect of the A. If for the B here is a 1 divided by 2n, also for the contrast of the B, for the AB will be equal to the contrast is a 1 divided by 2n. Okay. So through the two-way, the sign table here, you can easily get out the effect of the A and the B here. Okay. So this one is for the calculation of the effect here. Okay. And then for you to calculate the sum or square, if you still remember what we study the analysis of variance, we always need to calculate the sum or square. For example here, if for the two factor case, you need to have all the sum or square. So you have a sum or square for the A will be given by the B times n summation of the yi dot dot minus the overall mean. So this one is for the case of the factorial design. You're using this formula to calculate all your sum or square for all the component. And then because of 2 power of k factorial design also is a one special case under the factorial design. So therefore, the formula of this thing will be the similar. Just a Bn summation of the yi dot dot multiplied by the this one is a grand total square. So I let you see if you have only 2 levels, then how are you get the sum or square? By using the information from the contrast here. Okay, by using the information from the contrast here. Okay. So I show you when the A and the B is equal to 2 levels. So I substitute the A is 2, the B is 2, A is a 2 here. So we have here. So if we list it down, then of course we have a 2n here. And then you have a I is equal to 1. You have a first term plus the second term here. Okay, so you have a first term, this component plus the second term here. So of course here y bar I dot, this one will refer to the average value. Okay, average value. This one is actually is equal to the what you have before. Is just a yi dot the total under the cell of the I divided by the total observation you have inside there. Okay, if you can recall back what is the I dot dot here, if you refer to the I cell here, so you are divided. Okay, I may show you here. Okay. Yeah, you see the I dot dot here, you are referring to the I dot dot here. If y bar you are referring here, you divided by the Bn, because under this cell, you have a B observation and then the N observation under the cell here. Okay, so therefore, this thing you divided by the B times the N here. Okay, so the B here is always the 2. The N here is the number of observation. So therefore, this one you can see that is equal to the yi dot dot divided by 2N. So the 2 here is referred to the here. Okay, and then the y triple dot here will equal to the y triple dot, the average value is divided by total observation. You have total observation is A, B, N. So therefore, this one will be equal to 4n. 2 times 2 is 4. So therefore, you have a 4n here. Okay, the average value, I go to here. I have a 2 terms. And then this one is a total under the first one. Okay, under the first one of the total. Okay, under the first one of total, but before they get the first one of total, I just tell you that, okay, this formula, we can be simplified out. We can be expand it out. The square term here. Okay, so why I will have this thing, you can see from here, this one is a 2n here. This one is a 4n. So of course, I need to multiply by 2 here. I got the 2n here. And then because there is a square term here, or you can be put the don't want to multiply, you just here have a 2n, here is 4n, I have an extra 2 here. So therefore, the 2 is still maintained here. So because the 2n and 2n here, I can factor it out. So it's become 1 over 2n squared. So the 2n cancel with the 2n squared, you have the 2n at the bottom here. Okay, the 2n at the denominator here. And then because the 2n already factor out, therefore you only left is a y1 dot dot. Okay, so the y1 dot dot, if you can observe the, okay, I will show you here. Let's say I put it in the cell here. This one is a factor A. This one is a low level. This one is a -1 low level. This one is a high level. So here is a factor B. This one is a low level. This one is a high level. Okay. So you have here, and then this one is the first cell is a total for the first cell. This one is a total for the first. Here is a B. This one is a total at the high level is a A. This one is a AB. Okay. So this one is a cell. I have it in here so that I can explain to you y1 dot dot means that the total under the first one. Okay, the 1 dot dot, the first one is a 1 dot dot. Okay, the 1 dot dot means that is a total here. Total under the here is at the low level. 1 is at the low level, so you have a 1 plus a 1 plus b. So you have a 1 plus b here. Okay, so the y triple dot is the overall total. So overall total will be given by this thing overall total. Okay, so the y2 dot it means that for the A at the second level, because you have a first level and second level, the total, therefore you get the AB, A plus AB, you have here, minus away the remaining of the total square. Okay, so if you simplify this part before you take the square, you get the following form, and then plus the another component here. Then if you observe it, the 1 over 2 here, you also can bring it out. 1 over 2 here also can be factored out. You get the 4 here, so it's become the 8 here. Okay, and then you have a 1 A B A A B. This whole thing, and then this thing is will be the same. Okay, because of the square here, you can bring out the negative. You can combine them together. Okay, so these two total out become 2. So finally, you will get your sum of square for the A. Instead of using this formula to calculate, then we can have a following one. Okay, so I need you to see from here. This thing is for the factor A. This one is referred to their contrast. Okay, their contrast. Okay, for the factor A will be the A minus B minus 1. Okay, so this one will be similar to what you have before in the previous one, is their contrast. So how to get the contrast? The contrast is get from the table here. For the factor A is -1 plus A minus B plus AB. So you can get your contrast directly. Okay, so from the contrast itself, you can get the factor A is just 1 over 2n. For the, if you want to get the sum of square, you also based on the contrast square divided by 1 over 4n. Okay, so in general, I will say that the factor A, the sum of square for the factor A will be given by the sum of square for factor A will be given by the contrast square divided by 4n here. Okay, so we can be extend the idea to the sum of square for the B. Okay, the sum of square for B will be equal to the contrast for the B square divided by the 4n. Okay, so therefore the contrast for the B here is equal to the AB plus the B plus minus the A minus the 1 square divided by 4n. Then the last one will sum of square for AB. Okay, so you will get the following one. Okay, so instead of using the original formula to calculate, okay, or the original, if you use the factorial analysis, you need to expand this thing, then you get your sum of square. Okay, so under the special case, as long as you know the contrast, then you can find the sum of square directly. Okay, you can get the sum of square will given by the following one. Okay. So in the following example here, okay, based on the what you have seen before the example there, okay, then we can calculate all the sum of square here. Okay, so the sum of square, I think this one is an extra slide. I will use the same example here. Okay, later on remove the extra page here. So based on this example here, of course I can be just put in the Excel form. I key in the data in the Excel form. Okay, but I save it in the CSV file format. So this one, I just show you the data, how I store the data. Of course, this thing is for the previous chapter 3, chapter 4. I'm using chapter 3, chapter 4, and chapter 5. I also key in the data in the Excel form. But this one, I just show it to you. I key in the Excel form. So this is the data I have. I use a notation -1 and +1. It represents the low level and the high level. So all these things will repeat for 3 times. Okay, so if I just put in inside my I call the data as a CSV data, then after that I get the result of the summary statistic. Okay, then of course my final answer is I want to get is a ANOVA table. Okay, even though it's a 2 power of 2 factorial design. So this is the ANOVA table. After I do the calculation, I will get the sum of square for concentration. We are refer to the A here is a 208.33. So here I will refer to the factor A here. This one I refer to the factor B. This one I refer to the factor AB. Okay, so we have a factor A, factor B, and factor C, factor AB, sum of square, and then finally your residue. Okay. So again, for the calculation of here, when you calculate the sum of square for the total, okay, you are using the similar thing. You have a summation because you have a 3 levels. You sum it out for the yijk square minus the y triple dot square divided by APN. Okay, so the sum of square formula, no matter what type of design you're using, they always will be the same thing. You square for all the observation minus the grand total square divided by total observation here. Then you get your sum of square for total. Whereas for the sum of square for the A, you no need to use anymore the summation or this thing anymore because you list out in the contrast. And then you label it as a AB, A1, A, B, and AB. Then you can be found the contrast. Okay, then you square it out. Is divided by 4n. You will get your sum of square for A, where I show you before. Then after that, you get the sum of square for B. Then you no need to get the subtotal anymore. You can directly calculate the sum of square for the AB. Okay, just the contrast of the AB square divided by 4n. Then finally, you use your sum of square for the error. will be equal to sum of square for the total minus the okay, so you will get your sum of square for error for overall. So sum of square for error formula, they will keep changing, depends on what is the factors you have, how many factors you have. So therefore, the formula will be uncertain. Okay, so we are not going to memorize for the SSE formula for this design. What is a SSE? No need. You just need to know is you have a sum of square for total, and then you can calculate the sum of square for the remaining one. Then you can finally get the sum of square for error. Okay, so beside the sum of square, you also need the degree of freedom. The degree of freedom for sum of square for total always must be total observation minus by 1. So you have total is a 4 times 3 is a 12. So the degree of freedom for total will be 11. So this one will show it to you. The total degree of freedom as you can observe it, 8, 9, 10, 11, 11. Okay, the total degree of freedom will be 11. Okay. Then the degree of freedom for the A, because it's a 2 level, so always the degree of freedom must be 1. The B also 1. For the A, for the iteration AB, is a degree of freedom is just a A minus 1, B minus 1. This one is a B minus 1, minus 1. Okay, so this one is a ABN minus 1. So all these things is a degree of freedom. So all these things will be 1, the degree of freedom 1, the degree of freedom 1. So what you can see 1, 1, 1 here. Okay, and then of course the sum of square, we can use it to calculate out. Then you get your mean square. Finally, you get the F table, the F value here. Then from the F value, you can be checked whether which factor is important, which factor is not the important. So clearly, we know that the factor A, there is a significant difference. Means that are using the different factor levels, using the different level will lead you to the different values. But of course, we only have 2 levels. So whether we want to use a high level or low level, we need to check it carefully to test the, to check the plots, or we can compare with the multiple levels, is we can check it. So in this example, so we can the factor A, I should use a low level and a high level. But bear in mind that at the beginning of the chapter, I also have mentioned to you what we study is the 2 power k factorial design is very useful for the screening process. So we want to screen that whether you use a different level will lead you to the same conclusion. But for the factor here, to show you that there is a significant difference in their different level. Similarly, for the factor B, also there is a difference. Okay. So this one is the output from the Minitab. They also produce the same output, but in the Minitab, instead of using the here, they will produce for you is this table. But in the Minitab, they produce in this table, they will group all the mean effect together. So you cannot be find what is the sum or square from the factor A. They will group all together. Okay, for the two-way iteration, they group together because you only have one two-way iteration, therefore they have 1. For the mean effect, you have 2, therefore they group it together. Okay, so they will do it together instead of only 1 by 1. But of course, what we study, it should be, we only concentrate on 1 by 1. Okay, so this one is where the ANOVA table in the analytic Minitab, they are not complicated here. But of course, even though here you cannot get the information, but the information can get from the other here. Okay, it's a factor effect. Actually, from the factor effect, we can convert to the sum of square. Okay, so this one is the output from the Minitab. And then I recall back for you here. You see that the sum of square were using the contrast. Similarly, for the effect also using the contrast. So they are relationship in between the effect and the sum of square. If I given you the effect, you can calculate the sum of square. If I given you the sum of square, then you can calculate back the effect. Okay, so these two are the here. So I will stop for the half an hour. Okay, I will stop for half an hour. Then after that, we continue back our class. Okay, but for today, we only have a lecture class. We do not have a tutorial. Okay, so basically, I will have another later on after we continue back. We have another half an hour. Okay, if I cannot finish, then I will extend it to another 45 minutes. Yeah. Okay. Yeah. Okay. So I stop for the while first.